Welcome to our lesson 6 of Ionic Equilibrium. We are looking at weak acids. And in this lesson, we want to discuss how do you calculate the value of pH of a weak acid. Now, for stronger acids, once we are given concentration of a stronger acid, since they undergo complete ionization, we would simply now use the molar ratio depending on the basicity of the acid and get the concentration of hydrogen ions, as we saw in the previous videos. But for the weak acids, we cannot rely on the molar ratio because the whole amount of the acid does not dissociate. Part of it remains unionized. And therefore, given concentration is not enough for us to be able to determine the concentration of hydrogen ions in solution. And that's why we need the acid dissociation constant to help us determine the concentration of hydrogen ions and hence determine the pH. If we are not given the acid dissociation constant, then we need to know what we call the degree of ionization. Degree of ionization will tell us the percentage of every 1 mole that has ionized. But for this video, we are going to see how do we calculate the pH of a weak acid given the Ka value. When given the acid dissociation constant Ka of an acid and concentration of the acid, then the molar concentration of hydrogen ions can be determined. And hence pH. And hence pH of any acid. Consider a general ionization of a weak acid. Capital H, small, capital H, and capital A. If this is our weak acid, it could be an organic acid. HA, when dissolved in water, ionizes partially to give us hydroxonium ions and A minus aqueous. Now the Ka expression according to the law of mass action would be the molar concentration of the hydroxonium ions, which represent the hydrogen ions, times the molar concentration of A minus divided by the molar concentration of HA. We said that using the law of mass action, we eliminate the concentration of water because its concentration is relatively constant. It does not change since it's large excess. Now, the Ka expression is given. And we have said that if they have given us the Ka value and the concentration of the acid, then we can determine the concentration of the hydroxonium ions or hydrogen ions, and hence the pH value. But we see that in the expression there is the concentration of A minus. We cannot rely on molar ratio of the reactants to products to give us the concentration of A minus, because we don't know how much of the weak acid has ionized. If we knew how much, the degree of ionization, then it would be easier to get this. But since we do not know, we have some assumptions that we take when we are using Ka to determine the concentration of hydrogen ions. So the assumptions that we take, while using Ka value. Number one, we've already taken it. Number one, we ignore the concentration of water when rating the expression of Ka, since its concentration doesn't change or is constant. It's in large excess. Full stop. We've already taken that assumption in writing the Ka expression. Assumption number two, that at equilibrium, the concentration of the hydrogen ions, concentration of hydrogen ions or hydroxonium ions is equal to the concentration of A minus, the conjugate. That is true at equilibrium. Now, if that is true at equilibrium, and this is called an equilibrium constant, then we can rewrite this expression where the concentration of A minus that we do not need in determining the pH can be replaced by another concentration of hydrogen ions, since they are equal. So this modifies the Ka expression. This modifies Ka expression as Ka is equal to concentration of the hydroxonium ions squared, because now there are two. Even the position of A minus is taken by hydroxonium ions since they are equal, and this is not necessary in determining pH, over concentration of HA. And at this moment, we know the Ka value. We know this, and so we can determine the concentration of hydrogen ions. So the concentration of hydrogen ions or hydroxonium ions will equal to Ka multiplied by the concentration of the acid HA, and all this is under a root. That will be now near to getting our pH. Assumption number 3 that we take, and we shall see how important this is later, is that the degree of ionization of a weak acid is very small. We shall be seeing how this one we shall use it. And then also temperature is constant. Because Ka depends on temperature. When temperature varies, then Ka is bound to change. Now, if this is okay, then we shall look at some examples of how to calculate pH given Ka values. Examples. Example number 1, we have a weak acid called ethanoic acid. And the expression or the value of the ionization constant is 1.8 times 10 power negative 5. And the concentration is 0.05. Can we determine the pH? We are saying the acid dissociation constant. Dissociation constant, the acid dissociation constant of ethanoic acid is 1.8 times 10 power negative 5 moles per decimeter cubed. And the concentration of the acid is 0.05 molar. Can we determine the pH of ethanoic acid? Very easy. We shall say, when we are given that, the first thing that we shall do in the solution is write the equation for the ionization. Because from the equation of the ionization, we get the expression of Ka. So equation, ethanoic acid, when dissolved in water, partially ionizes. These must be reversible arrows to give us the ethanoate ions and hydroxonium ions. Alternatively, we could simply say ethanoic acid partially ionizes. Once it's aqueous, simply means it's dissolved in water, and so the water can always combine with the protons to give us ethanoate ions and the hydrogen ions, like that. So the Ka expression from this would be, using the above, this, the concentration of ethanoate ions times the concentration of the hydroxonium ions over the concentration of ethanoic acid. Now, we said after writing this expression, we've used the first assumption, ignored the concentration of water. Now we go to the second assumption, that at equilibrium, the concentration of ethanoate ions is equal to the concentration of the hydroxonium ions. Therefore, our Ka, which value is given, 1.8 times 10 power negative 5, is equal to the concentration of hydroxonium ions squared, because the space of ethanoate ions is equal to the concentration of ethanoate hydroxonium ions. So it can take up that place, and then it becomes double. Since ethanoate ions are not important in the determination of pH over the concentration of 0.05. So concentration of hydroxonium ions would now be equal to 1.8 times 10 power negative 5 times 0.05. And the calculator that we are using, you compute, use the brackets well, 0.05 times 1.8 times 10 power negative 5. That should give us a concentration of around 9.48 times 10 power negative 4. This is times 10 power negative 4 moles per decimeter cubed. Now, after getting the concentration of the hydrogen ions, then we go ahead and determine the pH, because pH is defined as the negative logarithm to base 10 of the concentration of hydrogen ions. So pH is negative log base 10 to the molar concentration of hydroxonium ions, or negative log to base 10 concentration of hydrogen ions. No problem. Now, we can substitute. So pH is negative log base 10, open brackets, of 9.48 times 10 power negative 4. So you get our calculator, and then we press negative log to base 10 of the molar concentration, which is 9.48 times 10. Now, a hint. Since these are weak acids, the value of pH we get must be less than 7. And you can try and prove whether it is 3.2, but I got 3.2 when I press using the calculator. 3.02 rather. 3.02. And this value is likely to be correct, or is correct, because it is actually less than 7. The pH of weak acids must be less than 7. So that is how we determine the pH of weak acids using Ka. And this could be followed with questions like state the assumptions used in your calculation. In that case, if they say state the assumptions used in your calculation, then you're going to write each of the assumptions as we stated them, that using Ka, the following assumptions are stated, and give them according the way you use them. Give them in that order. For example, the first one we said, we ignore the concentration of water when writing the expression of Ka, since its concentration does not change. Number 1. And we have rightly used it when we're writing this expression. Another assumption that we've taken is that at equilibrium, this is only correct at equilibrium. At equilibrium, the concentration of the ethanoate ions is equal to the concentration of the hydroxonium ions, and that is very helpful in us getting the concentration of hydrogen ions. Number 2, we said the degree of ionization of a weak acid is very small. And lastly, temperature is constant. Those are the assumptions we take. If they have been asked, then you rightly put them. Don't write them mathematically like this. Write in words. This is how we use Ka value to calculate the pH of a weak acid. In the next lesson, or next video, we shall be looking at how we use the percentage dissociation or degree of dissociation together with Ka to determine the pH of an acid. Thank you for watching. See you.